Engineer Janath, can you hear me? Engineer Janath, can you hear my voice? Engineer Tushar? Engineer Tushar, can you hear my voice?
Mohan, we can hear well, Mohan.
Right. Thank you. Thank you. Okay. 6-1. We will wait 1 minute and we start.
Okay.
Right. Good evening. Good evening, all. On behalf of Building Service Engineering Sectional Committee, I would like to warmly welcome you all for the today's session. As a Building Service Engineering Sectional Committee of IESL, we conduct these kind of lectures, webinars for all of us to gain knowledge on modern technologies and the subsequent topics. So today also one of the most important topics we brought to discuss with good lecturer. So today topic is setting the standard for net zero building. Why it is important in the current context? It is mainly for the climate change. If I shortly explain a little bit, in 2015, Paris Agreement, 197 countries came into agreement to come back on climate change to reduce the greenhouse gas emission. So that means we have to limit the global temperature rise 1.5 Celsius. That is our target. So in the Paris Agreement, Sri Lanka also agreed to reduce to net zero the greenhouse gas emission 2050. The emission to be zero. That means the amount that we produce and amount we set off against the produce should be balance it off. That is our requirement. And in 2050 at the net zero target. So to reduce the global warming impact, I think you know last year was the hottest year in the global world, 2024. It already surpassed their set target 1.5 degrees Celsius increase. So we all are in alarming condition in the climate change. So it is the right time to discuss these things on lengthy topic because climate change is inevitable and it is a real. Everyone has to face this climate change impacts. So as engineers and other professionals, we have to give certain contribution to our society and the environment to control the greenhouse gas emissions and all. So as a professionals and engineers, we do develop buildings and many factories. So when we are doing those designs and factory designs, we need to think nowadays not only the energy efficiency, but also impact on the greenhouse gas emission that it has a broad meaning, not only energy efficient aspect. So to bring these topics into the current discussions, we thought to bring this topic today, the setting the standard for net zero building. So today we have a very good lecturer for discuss this topic. So I will invite Engineer Tushan Gunaratna to introduce the today's topic and the modern resource person to the audience. Engineer Tushan, over to you. Engineer Tushan. Hello. I think Engineer Tushan is microphone. There's a issue with the network. So without wasting time, I will directly invite Engineer Chandana Dalugoda to is a today's resource person, is an engineer, well expert in this field and the visiting lecturer and this field, HVAC field, very prominent industry expert. So I will invite Engineer Chandana Dalugoda to start the session today. Engineer Chandana Dalugoda, it's over to you.
Thank you, Engineer Mohan. Thank you very much. Just give me a second. All are welcome today for this little talk on setting the standards for net zero buildings. This net zero term is being used quite often now. Let's dig into this and see how and what we are mean about this. These are the contents we are going to discuss today briefly. Why net zero matters? What is a net zero building? Key principles, setting the standard, challenges, and case studies. There are so many case studies, but I took one case study. Role of stakeholders and Sri Lankan roadmap, where we are. Net zero buildings are really beneficial because they reduce energy costs, of course, minimize environmental impact, like in a green building, increases the value and desirability of the building that go beyond a normal green building. They also contribute to a healthier indoor environment and can improve companies' profile by demonstrating commitment to sustainability. There are many advantages we can categorize into three areas. Environmental advantages, that is reduced carbon footprint of your building. Now, what is carbon footprint? It is energy use by the building for the entire year. And the effect of carbon emissions in carbon dioxide equivalent tons per annum is called carbon footprint. Now, in your house, you can calculate your carbon footprint. As a matter of fact, if you have a kilowatt hours data for January to December, you add all that annual kilowatt hours and multiply by the factor which is given by, now we have a mix. If it is diesel power, about 2.58 10 to the power 4, I can't remember now. This is our one is a mix 5.8. So likewise, we can find the carbon, tons of carbon equivalent emission due to our building. So reduction is what is we are talking here. Then reduce reliance on fossil fuel, improved indoor air quality. Now these are the environmental advantages. Economic advantages: reduce energy costs, future-proofed assets, increase asset value and desirability. Social and business, that is healthier buildings, improved company profile, meeting climate goals. You are complying with national goals. So that is why net zero building is required. Now, climate change, as Engineer Mohan said, climate change, I think in Buddhism, Lord Buddha has even told certain years later that the entire earth will come to a burning situation. Now that is going to be true in time to come, because our surface temperature is increasing alarmingly due to emissions, especially emissions. So global warming potential is discussed very much. We'll have to use refrigerants, especially with global warming potential, low global warming potential. What happened was we had a problem before. Ozone layer is attacked by chlorofluorocarbons. So chlorofluorocarbons were taken out, banned, and HFC refrigerants were introduced, and we were very happily living. But then later we found HFC have another effect called global warming. So the indices global warming potential came. When we select refrigerants, we'll have to find very low global warming potential refrigerants. Now the best one is ammonia, and then we have R1234. Why is it now? It is 1 global warming potential is 1. R32 global warming potential 50. Now those things. So the net effect is 40% of global carbon emissions account for buildings. That is the problem. So built environment has to answer. Emissions come from construction of buildings. We call embodied carbon. And operation of the building, such as heating, cooling, lighting. Now that falls to operational carbon. Now we'll have to reduce both embodied carbon and operational carbon for the life cycle of that building. That is the aim. As we know, rapid urbanization is happening all over the world. That means growing energy demand. So we need decarbonization. Decarbonization. So decarbonization of buildings. Now that is an essential item to meet climate goals. As we know, Paris Agreement, as Engineer Mohan mentioned, 1.5 C limits below 2 degrees C will have to maintain. So all the aims are on that, curtailing HCFC and HFC refrigerants and also global target of reaching net zero by 2050. Now, this pie chart shows the global emissions. I'm not going to go through all that. Electricity and the heat production is 31%. Fugitive emissions, that is hidden emissions, about 6%. Transportation, manufacturing, all that is there. Those are the culprits. Now, 16% of transportation, 12% manufacturing and construction, and also agriculture, like that. So, climate change is driven by human activity, surely. Now, things like burning fossil fuels, construction and operation of buildings account to 40%, as I told, out of which about 28% is operational carbon, and 12% of embodied. What happens? Our total rainfall and total climatic positions are changing. Due to temperature increase, ice caps are melting, so sea level increasing. I doubt very much how we are going to continue with our acquired land in Colombo, port city, in time to come, because water level is rising. Now, net zero building, is it a necessity? Yes, it is a necessity, not just a requirement. As the global population grow and urbanizes, energy demand will increase. So the way we design and operate buildings must fundamentally change. So net zero buildings are not just a trend, but it is merely a necessity. Global carbon targets and deadlines. Now, by 2030, 100% of new building must be net zero carbon in operation. Now you'll have to you will come to see this net zero carbon, net zero energy, two things at the same time we are addressing. So by 2030, 100% of new buildings must be net zero carbon in operation. And embodied carbon must be reduced by at least 40%, all these for new buildings. By 2050, all new and existing assets must be net zero across the whole life cycle of that building. These are the carbon targets. So if we define net zero in the built environment, it refers to a building or a project has zero or negative carbon emissions over its entire life cycle. Entire life cycle. That is including construction, operation, and end of life. There's a latest ASHRAE standard 100 in 2024, energy emissions building performance standard for existing buildings. What it does? It provides processes and procedures for reducing energy consumption and carbon emissions through improved energy efficiency and performance of buildings. all existing buildings, including residential, commercial, institutional, and industrial. Okay, so we were discussing all about net zero. So ultimately, what is a net zero building? As I told you, there are two terms we are taking here. The energy balance concept in the built environment refers to a building's net energy consumption, where the energy input, that is generation, and the energy output that is used has to be in equilibrium. A net zero energy building, therefore, a building generates enough renewable energy on site to cover its total energy demand. Whereas net zero carbon buildings, carbon emissions throughout the building's life cycle, including construction, operation to end of life. So the carbon emissions has to be zero. So the operational versus embodied carbon is operational carbon refers to emissions resulting from buildings' daily operations, such as heating, cooling, lighting, and running appliances, like in our home or office. Embodied carbon, on the other hand, is the emissions associated with the manufacturing, transportation, and assembly of building materials. That's why in building certification programs, you get more credits if you source material in the local area. Say, if we are building a complex in Colombo, we are going in for bricks. We can get these bricks cheaply from, say, Anuradhapura. Or some are available in Kaduwela. Or some are available in, say, Dalugoda, very close by. What happens? Your transportation, distances are getting lesser and lesser. Carbon emissions are lesser and lesser. Now, this is a diagram gives you net zero carbon buildings definitions. This is from World Green Building Council. Now, we are talking about whole life carbon. And if you take a building, what you can see here, a building, we are talking two types here, operational carbon and embodied carbon. If operational carbon of the building, a baseline, is this much of operational carbon, that means this much of carbon dioxide tons equivalent. Now, going into net zero, first step is energy efficiency measures. So you'll have to reduce energy efficiency. Now, for instance, a green building, we reduce energy by 30%. But going for net zero, we are supposed to reduce energy well below 50%, up to 90%. We'll have to first reduce. Now, people think just because you have a solar PV on your rooftop, it is a net zero building and it helps reduce emissions. No, first you'll have to reduce energy. So your benchmark, when you reach that level, you call that is an energy efficient building. That is energy efficient building. Now, next step, you use renewable energy. Now, in Sri Lanka, moment we call renewable energy, it is solar PV. But we hear wind energy, but we don't hear a geothermal. But other countries, now if you take UK for that matter, normal projects, you have these three renewable items plugged in. Where we go wrong in Sri Lanka, we think wind means the monster size windmills. No, we are talking about 1 kilowatt, 5 kilowatt wind mill, small windmill in your building. So this light blue cyan color shows you some on-site renewable energy with your normal energy consumption. So that becomes now nearly net zero energy building because 75% is renewable energy. By chance, if you can have 100% on-site renewable energy, we call that building zero energy building. We call zero energy building. But if you can have more than the required renewable energy to offset that building called energy positive building. Now the next step is some on-site plus some off-site renewable energy is added. Now that becomes net zero operational carbon building with 100% off-site imported renewable energy from another site, but dedicated to your building. So now you have got net zero status, but still not the whole life carbon reduction because you have your embodied carbon already. We have to reduce embodied carbon up to a certain extent and compensate for residual emissions as well with renewable energy. That becomes net zero whole life carbon. You can have carbon offsets like that. So this is how the entire definitions looks. Certifications and frameworks. Do we have net zero certifications? Yes, we have net zero certifications. One is LEED. We are very conversant with LEED. We have LEED certification. In that, the latest one is LEED Zero. And there's another certification authority called Passive House. That is from Germany. That is much more stringent than LEED from US. Now, if we just go into the LEED net zero program, they have 4 areas: LEED zero energy, LEED zero water, LEED zero carbon, and LEED zero waste. 4 things. Say LEED zero energy. What does it mean? LEED zero energy. Buildings that achieve a source energy use balance of 0 for the past year. Source energy balance equal total energy delivered minus total non-renewable energy displaced. Either you must have minus or equilibrium. Lead 0 water, similar. Water balance is total potable water consumed minus total alternative water used plus water returned to original sources. So that means buildings that achieve a potable water use balance of 0 for the past whole year. 0 carbon, also same. Carbon dioxide equivalent must be 0 or negative. Carbon balance equal total carbon emitted minus total carbon avoided. Finally, lead has 0 waste. Achieve true 0 waste in the platinum certification level. So these are the standards from LEED 0. And passive house certification. That is becoming very popular in the world. Very, very stringent. If somebody asks what would be the cost, incremental cost to get a net zero building, I don't talk. We should not look at that way because our aim is to reduce climate effects and to live longer. So coming back, passive house certification, example, heating and cooling related energy savings up to 90% compared with the typical building stock, over 75% compared with average buildings. Now you can see on this little sketch, low energy house has 75 kilowatt hour per square meter per annum energy for heating, but passive house will have only 25% or 15%. That is how passive house certification is implied and how we target, how we design the building. Now coming back to high level of comfort, they use energy source inside the building. For heating, they use heat from people. Appropriate windows with good insulation, and building shell consists of well-insulated exterior walls, roof, floor slabs. Of course, we do all that in green buildings to a limit. We all are talking, but no results. We don't go up to that level. A ventilation system consistently supply fresh air, making for superior air quality without causing any unpleasant drafts. So that kind of important aspects of passive house certifications. Now you haven't heard passive house, I think, but I'll give you a very good example of passive house certification. Now this is a case study of passive house, Stargaman Innovation Center, Sri Lanka. Will you believe this project is the first passive house project in South Asia? And importantly, one of only 2 certified buildings, passive house, in the entire world. Achievements: annual energy consumption will be cut by 75% compared to conventional, efficient, modern buildings. So you can see the passive house certification. The client, Star Garments, I think you have heard, these Katnayaka IPZ factory, but the portion converted to a innovation center. Architect Jordan Paramas from Digital Architecture USA. Building services consultant from Sri Lanka, that is Chandana Dalugoda consultant. So I was real proud to be associated with this energy consultant Stephen Winter Associates of US. What are the credible achievements? Cooling and humidification demand, kilowatt hours per square meter annum, 183. I just have had a small calculation to see Sri Lankan context. 250 watts per square meter. There's a normal cooling load for a building. What would be the figure here for Sri Lankan context? It will be about 720. 720 has dropped to 183. So that is called a passive house. These are net zero buildings. Okay. Key principles of net zero carbon designs. What are the key principles? Renewable energy integration. That is a must. Rooftop solar, it is happening now. Small windmills of buildings, not happening. But on the other hand, our situation is such that, especially Colombo area, during summer, our wind velocities are quite low compared to other countries. So we are thinking of small windmills, not monsters, and geothermal as well. So solar energy storage is a must. Solar PV system energy storage is essential for achieving net zero energy usage, energy goals. So what are the benefits? Energy storage. Battery storage allows excess solar energy to generated during the day to be stored, of course, and used later. That is, we know. But especially when the sun is not shining or for night, this ensures a consistent energy supply even when solar generation fluctuates. That is our problem here. Grid stability. Battery storage can help stabilize the power grid by absorbing excess energy from solar and releasing it when needed. Improving grid resilience and reliability. I think this is how it looks if you take grid supply, let's say 1 megawatt, throughout the day time straight. But for solar cumulative load, solar load is like this. Now the problem is, now these areas, who will support the grid? Or the grid has to be plugged in with small generations. But if you have battery pack, we can fill all this and you can have a very balanced power supply. So grid stability can be achieved. And peak shaving, you can shave the peak as well. Battery storage can help reduce peak demand on the grid by storing and releasing energy during peak usage periods, leading to lower energy costs. Now, geothermal energy, not used in Sri Lanka as far as I know, but in UK, every project, a large project, you have geothermal energy. I was working with a consultancy firm. Every building, the building that we did, had geothermal energy, wind and solar PV, small amounts. But the contribution is big with these three. What is geothermal? You use earth heat storage. During summer, you pump It can be a brine solution. A earth stock will be absorbing heat. So the condenser is inside the earth. A evaporator is in the building side. In the winter, the vice versa, a earth stock has the evaporator and the heat dissipation to the building by using of heat pumps. So geothermal in small scale should be used for a building. So all these renewable three ways has to be used for net zero buildings. Of course, we have smart systems and an energy management area, data analytics, and Internet of Things can be used for HVAC performance monitoring, like IoT-enabled sensors and devices to collect and transmit data from HVAC system across the building. Enable remote monitoring and control via smart devices and cloud platforms. Then the centralized data management using BMS, IoT platforms aggregate data from multiple HVAC components into unified dashboard is available. So IoT plays a role. And the BMS. Quite unfortunately, BMS in Sri Lanka is just merely a showpiece. They look at the monitor, your chiller is working, the fans are moving, rotating, the pumps are rotating, all on off and monitoring purposes. No, what we are talking about, energy saving strategies has to be used with a BMS. Now this BMS output, I took this on a weekday, almost 2 p.m. Almost 2 p.m. Now you will see the chiller loading is only 71% at 2 p.m., the peak, thanks to BMS operation with various energy saving strategies. I'm going to discuss these things quickly. First one is chill water reset. As you know, chill water temperature is governed by AHRI standard. It is originated as chill water out 44 and return 54. That is in centigrade, it is 6 degrees, 6.6 and 12.2 degrees respectively. Why it is 6 degrees out? Because water is freezing. Not at 0, mind you, even 2-3 degrees water start freezing. So the safe minimum is 4.55. So better it is 6 degrees C. On the other hand, why return temperature should be 12? Because return temperature governs the dew point temperature of the cooling coil in the room. This 12 degrees, the maximum allowable is 13 degrees C to achieve 50 RH in the room. So dew point 13 is the highest before you rise the RH. So to save side 12. So chiller is operating 612, but now there are different standards, not 5K difference. You can go for 8K difference, but keeping 12 degrees return same, but chiller out is about 5 degrees C. 5 and 13. 5 and 13 to get 8K. That is another good way of operating. So chill water reset is something else. Chill water reset is your outlet temperature 6 degrees. We can raise during part load conditions. What is part load conditions? Surely not in the morning, but afternoon, in the evening, probably 4 o'clock to 5 o'clock. During night. This is 24-hour operation. During night, rainy day, you can raise the temperature, but with closely monitoring your dew point temperature. If it increases, your relative humidity cannot be met. The benefit is you get 1 to 1.5% chiller energy saving, directly proportional to your living temperature. Fan cycling. Fans are working constantly throughout the day, wasting energy. Sometimes you can reduce the airflow. Now the VFDs are very common and very cheaply available. Why not use cycle fans? Duty cycling, another energy saving strategy using BMS. This is to avoid setting unnecessary electrical demand peaks caused by synchronous equipment on times. That is called duty cycling. You stagger the startups. Optimum start-stop. Now you can, in this picture, you can see building operational occupied hours. It is about 7 o'clock to 5 o'clock. 7 to 5 kind of a thing. You can also, this is the operational time. Equipment operation with optimal start-stop. You can stop the air conditioner slightly ahead of time, but you start the air conditioner pretty much ahead to pre-cool the building. Now in Sri Lanka, we have done so many improvements of buildings. I'll give you this. Usually Monday to Friday, 8 hours of building operation. Say building has 1,000 kilowatt hours every day. So you think 5,000 kilowatt hours for 5 days when you run 8 hours. But if you start, now this is 8 a.m., 5 p.m. But now you start 6 a.m. and run to 5 p.m. 11 hours instead of 8 hours. For Monday, Tuesday, probably Wednesday, you come back to 7, Thursday, Friday, 8 hours. Now, what you think, 5,000 hours, now it has gone to 7,000 hours, obviously. No, 6 a.m. Monday, you pre-cool the building before occupation. Before all the computers and equipment running, you pre-cool. Effect would be this 5,000 can be dropped to easily 4,000 kilowatt hours. That is really happening. Now we are doing this in Ceylon Towers. One of the jobs that I just completed, Sampat Bank building, we are doing this. Enormous savings, optimum start-stop. Unoccupied ventilation, night purge. This is another function that we should do. Obviously, we have to pre-plan this. HUs will run in the night for a short period without refrigeration, taking outdoor air into the building, sweep through the building and exhaust. As you know, outdoor temperatures are plummeting Now 32, 33, 34 during day, and it is going down 28, 26, sometimes end up at 24 in the late night, morning. So use 24 degrees C air and pre-cool the building. You'll have to design this properly. You'll have to design this properly. How to take your fresh air, 100% supply air quantity, and exhaust also 100% supply air quantity is largest. So all that has to be done methodically. BMS is initiating this, called unoccupied ventilation. Electrical demand limiting. It's a nice function. I don't know. Most of these BMS suppliers haven't heard of these things. I don't know. When the demand rise over the previous demand charges limit, preset limit, now this is increasing. BMS is tracking this, and predetermined time send a signal to all the DDCs where HU set point increase by 1 degree C. Set point 24 now to 25 C. A large building. I will take example, Sampath Bank head office building. There we have 66 HUs. Mind you, all 66 HUs, set point increases to 25, instantly chillers will unload. So you shave the limiting. Now, those are the building management system energy saving strategies. There are so many other things. I just selected few things. These are in my lectures in the university. So you'll have to implement these. Coming back, materials and embodied carbon consideration. How embodied carbon comes into play. You can see in this picture, production phase, 65 to 85% embodied carbon getting into the building materials. Construction phase, about 10%. Use and maintenance phase, very long time usage, only 15%. End of life phase, about 15%. Why? Why we are worried? Because embodied carbon account for 11% of greenhouse gas emissions. So, net zero buildings, energy saving is the first. Without doing anything, try to achieve passive designs as much as possible. Passive designs. By reducing energy 50%, how? Few things like reoriented building, if it is a new building. Align the north-south axis, your longer side. Shorter side of the building facing east and west. Another one is external shading for windows. Maximize natural ventilation methods, single-sided, double-sided, and stack. But this is only naturally conditioned spaces. We call naturally conditioned areas. Surely not Colombo. Not Colombo. We'll see later. The other thing is building envelope heat gain, loss reduction. Use AAC concrete. AAC concrete. Can you see the thermal conductivity reduction, AAC? Brick 0.81, AAC is 0.12. Use low E glasses. Low E glasses, double pane, triple pane, double pane glasses at least. Thermal insulation for roof. Comply 90.1 ASHRAE. Tile roof for Sri Lankan climate zone 0, you need 8 inches. Will you believe? Cool roof design. What is cool roof? Reflective roofs. In fact, one of the exhibitions, I told these roof manufacturers, why you all up having red color, green color, blue color? Have it white, silver color roofs that will reflect sun's heat, called cool roof. And continuous air barrier system. Can you see air barrier? This is the air barrier around the entire building. So air barrier we had at the innovative center, Star Garments. That will stop infiltration and exfiltration. So passive design reorientation we discussed. Projections, you can see the projections here. These are projection. You might think, oh, come on, this is common. But the implication, the PF should be, as per 90.1 for energy efficiency, PF for the first story should be 0.5. PF for other stories, you can go up to 0.25. PF is the projection factor, the width of the awning divided by the height. When the PF factor become increasing, your multiplier, solar heat gain coefficient multiplier reduces. That means your heat transfer reduces. Climate zones. ASHRAE 169, World Climate Zone, Sri Lanka. Now we have got, we are very proud now, we have got 8, is it 8? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 locations. In the standard, early it was only Katunayaka. Now we have got 12 locations. Most of the locations are a climate zone 0A. Even Colombo, Rakmalana, Gol, Hambantota, Trincomalee is 0A. But we have 1A and 3A, Kandy and Nuwara respectively. Now these areas are conducive for natural ventilation. So passive cooling methods can be introduced in these areas. Single-sided ventilation. Now, theoretically, single-sided can be effective only. The width of the room is 2h, maximum 2h. H is what? H is height. Width is 2h. If it is double-sided, you can go up to 5h. Or stack effect. Stack. This is very common in Britain. Even Nuwara, British buildings in Sri Lanka, you have. In my house, I built a stack thanks to my architect, and this stack effect is happening in an enormous way. Cold air going through this and discharge. So entire building is getting naturally ventilated. Next one is setting the standard frameworks and matrix. We'll see what are the frameworks. So net zero energy standards of the building often express the units kilowatt hour per square meter. per year. Per year. This is aimed to minimize energy consumption and achieve carbon neutrality. Now, new homes are in the range of 35 to 40, out of which about coal countries, 15 kilowatt hours per square meter per year is for heating alone. We have a policy benchmark, that is ASHRAE latest standard, standard 228/2023, standard method of evaluating zero net energy and zero net carbon building performance. So ASHRAE standard is there. Challenges in achieving net zero carbon. Of course, big challenge, the economy wise. Well, upfront, there will be higher costs. Green building, 20 to 25% of a normal building. Net zero building will be much, much higher. Long payback period. Limited architectural options sometimes. These are the limitations. Technical complexity. Potential space limitations sometimes. Well, initial learning curve, we'll have to go through that. Then limited availability of skilled professionals also could be a limitation. Building net zero buildings typically cost $175 to $180 per square feet. Now that is coming to 50,000 rupees if it is it? $180, let's say 180 is about 54,000 rupees per square foot. This is very, very high. Anyway, that is our target. Regulatory and policy gaps. Now, there could be policy gaps. Regulatory and policy gaps significantly hinder widespread adoption of net zero buildings. These gaps include lack of mandatory reporting and reduction of emissions, inconsistent policies, and lack of clear mandates for green building practices. Fortunately, in Sri Lanka, we have Green Building Council. That is a signatory of World Green Building Council that supports all these. Okay, we'll go through a case study. This is Unisphere building, the world's largest commercial net zero building in the United States. This is just a small clip. We'll go through this. Hope you can see this. The shading automatic of the glasses. Geothermal energy is used. Okay, we'll take one by one the key areas. Solar photovoltaic. Now they have 3,000 plus high efficiency solar panels, giving 1 megawatt of power for this building. Also, 52 geothermal wells, more than 500 feet into the earth, will be used to increase the efficiency of the heating and cooling system between 25% to 50% efficient. This system cycles hot and cold water depending on the season, used in the HVAC system through the wells, which act as a heat exchanger with the earth. The important thing is use of high performance windows, electrochromic envelope they call. Increased insulation, triple pane glazing, and electrochromic tinting glass. Automatically tint is changing, which tints more or less depending on the location of the sun. Will target 25% thermal improvement over minimum code values. This electrochromic glasses changes tint based on variety of factors, including season, location of the sun, cloud coverage, glare of adjacent structures, and the tenant preferences. Earth couple heating and cooling. Intake air into the atrium will be routed through an underground concrete labyrinth located beneath of parking garage. I don't think this is an innovative thing because Sri Lanka, I was told there's a old mansion here in Kaluthara. They have used, in fact, I want to have a little research as well there. Cold river air is introduced through the labyrinth and taking upwards, cooling entire building. Natural ventilation, stack effect is used during seasons, not every day, seasons. Centralized controls, BMS, effectively used. Daylight harvesting, they are using high ceiling paired with high light transmitters glazing located near the ceiling and out of the shadow of the facade mounted solar panels. So this is a classic example of a net zero building. As a matter of fact, ASHRAE, American Society of Heating, Refrigerating and Air Conditioning Engineers, US, that is one of the largest, not one of the, it is the largest international engineering institution, having 50,000 members in 190 countries. Their head office building, in fact, I have gone to that head office building. That was a green building. There was a tour, green building. Now they have gone into a new building, net zero. Of course, ASHRAE is talking about net zero. ASHRAE has net zero standards. Their own building is net zero. Right, role of stakeholders. All these stakeholders have their part: clients, owners, designers, architects, and contractors, builders. I don't go through all these. Government and policymakers, government and regulatory bodies. Yes, that is, government and regulatory bodies can play a critical role by enacting policies and incentives also to promote net zero. They can also establish standards and guidelines for building design and construction. Unfortunately, Sri Lanka, we are still trying to get our own building code. So we have a little bit of constraints here. Finally, carbon net zero 2050, Sri Lankan roadmap and the strategic plan. I'm sure you don't value Sri Lanka. You don't value Sri Lanka. Sri Lanka already in 2021, 2020, they set this target. That is carbon net zero 2050. We are ahead of others. We are par with others. It is great. Now, if you talk about the background, Sri Lanka is a low carbon emitting country with approximately 1.02 carbon dioxide equivalent tons per person. Now, this is coming from this net zero 2050 roadmap. But I'm comparing this to world other countries. The source is Worldometer. In that Worldometer, Sri Lanka carbon emission is 0.8. It is not 1.8, but let it be. Now, China is the biggest culprit, 32.8 carbon dioxide equivalent tons per person. USA 12.6, India 6.9, Russia 4.9, Japan 2.8, Germany great 1.7, Canada 1.5, South Africa 1, Australia 1. Importantly, UK is 0.8 as Sri Lanka. Thailand 0.7, mind you, Malaysia 0.7, UAE 0.5. So we'll have to reduce carbon emitting, although we are less carbon emitting country. We'll have to go forward. But unfortunately, we observe an increasing trend in CO2 in time to come. As a signatory to the Paris Agreement on climate change, Sri Lanka has committed to supporting global efforts to hold the increases of temperature in the average global temperature to well below 2 degrees C. That is a Paris Agreement. This is 2 degrees above pre-industrial levels. And to pursue efforts to limit temperature increase to 1.5 C above pre-industrial levels. So Sri Lanka's commitment. Sri Lanka has pledged to achieve net zero carbon status by 2050. I'm sure some people are laughing at this. No, but as a decent citizen, we should work towards in small way. By 2050, we should achieve carbon a net zero states. Now, this is in national determined contribution. NDC is a commitment submitted to the United Nations framework in 2021. So we have already committed. On the other hand, Sri Lanka is classified as lower middle income country, and its economy is largely dependent on service sector, 59.7 of the GDP. Of course, we can see our peak demand of energy is during night. That is the lighting load, service sector. So service sector is 59.7 of the GDP, followed by industrial sector 26.2 and agricultural 8.4. In 2020, CO2 emissions per capita for Sri Lanka had reached a value of 0.996 tons through a gradual increase from a value of 0.22 in 1990. So that means in 1992, 2020, 30 years, we have shot up 0.2 to 0.9, almost 1 carbon emissions per capita. So that is a bad sign. The mitigation actions presented in the updated NDCs reflect improved target setting in 6 sectors. That's a good to hear. There are 6 sectors. Energy sector, that is power, electricity generation, and end use. Then transport, industry, waste, forestry, and agriculture. At least we are going in the right direction. Enhance ambitions, including reducing GHG emissions by 14.5% and increasing forest cover to 32% by 2030. See how nice. We are really focusing. Again, our ambitions are GHG emissions reduction by 14.5% and increasing forest cover to 32% by 2030. To realize this ambition target, Sri Lanka further committed to achieve 70% renewable energy in electricity by 2030. Now CEB has to gear fast. Achieve carbon neutrality by 2050 in electricity generation and no further capacity addition of coal power plants in future. This is our Sri Lankan pathway. Sri Lanka has pledged to achieve economy-wide net zero carbon status by 2050. Thus, Carbon Net Zero 2050 roadmap and strategic plan for Sri Lanka attempts to create an avenue towards just transition to net zero pathways. Don't blame Sri Lankan authorities always. No, we are heading somewhat good. So this is all about net zero target. Finally, we come to 2 slides. This is baseline scenario of Sri Lankan situation, GHG emissions. This is the zero level, that is forest. Sequestration is absorbing CO2 carbon dioxide by forest. 2025, that is this year, but that is gradually increasing. But net zero scenario from 10,000 equivalent tons of carbon dioxide is dropping well below zero. That is our target. So this is all about today's discussion. If you have any questions, you can take it now.
Thank you very much, Engineer Chandana Dalugoda, and it's a great presentation. And thank you very much for sharing your valuable knowledge, and also as I'm working at water board, and that also we are implementing your ideas, and we gain a lot of things, and I'm asking to others also to implement these things and gain your companies and those things. And there are a few questions, but lack of the time, therefore I'm selected 2 questions. One is from the engineer Janath, and he asking that how do seasonal variation affect for the net zero buildings, sir?
Yeah, that is seasonal variations like that affect from renewable energy, because if you Actually, the people are blaming electricity board for unbalanced situation. But if you own a rooftop solar, you would see how the generation it is like this. CB generation is straight line. Now, can you depend on this changes? Now, this is daily changes, seasonal changes. Rainy season, then cloudy season. If the renewable energy, wind, you have a problem. Lack of wind. Now, all these things affecting net zero applications. That's why we have another component, off-site renewable energy addition to your building to compensate all this, to compensate. So seasonal effects, seasonal problems are affecting, but it can overcome by a off-site renewable energy plugging into the building.
Thank you, sir. The other question is from Engineer Gunaratna. What are the standard energy usages benchmark value for commercial buildings in Sri Lanka context?
Well, that I can't really answer exactly. That also heavily depend on the various things. Now you're asking normal buildings, not net zero buildings, normal buildings. That is because we don't have a building code. We don't have a building code. People produce buildings. Some are slightly considering energy efficiency, some are really not, some are going for certifications. So the benchmarking is there. What we do when we do a green building, we benchmark power consumption against the area. So I can't give you any norms as such for Sri Lankan context, but we can find our own benchmarking, like let's say 40,000 square meter building. What is the annual power consumption against 40,000 square meter building, certified building? What is the energy? And that kind of thing we can do.
Thank you very much, sir. Due to the lack of time, Engineer Janat, it is for you. Engineer Janat. Anyway, sir, thank you very much, sir. Yes, it is for you.
Kalna, thank you very much. Good evening, everyone. I hope you all have an inspiring and interesting lecture today. So now it's time to show our appreciation to those who helped make this event successful. First of all, I would like to thank our resource person today, Engineer Chandana Dalugoda, for accept our invitation and sharing sometimes untouched topic today, and also the content. We really appreciate your contribution, sir, for present this insightful lecture. So then further, I would like to present this virtual token of appreciation to J. Chandana Kalugoda. Dear sir, please accept this virtual token of appreciation. And also, I would like to extend our thanks to IS staff and the building service engineering section committee members for their support for organizing this event today. Finally, thank you all the participants for joining with us today by dedicating your valuable time. Thank you once again. We look forward to your continued participation in future events as well. Thank you very much. Good night, all.
Thank you.
Thank you.
Thank you, sir. Good night, sir.
Thank you, sir.
Good night. Good night.